Okay, well, this is the first file structure that we're going to look at. Ostensibly, we're talking about selection, but we also want to look at other operations that change the data in the file. Okay, so a heap file is, we've seen plenty of examples of that before, but basically a sequence of pages. Each page contains tuples. In the diagram, it looks like all the tuples are the same size, but that's not necessarily required. Other important thing, there's no particular ordering of tuples. It's possible that insertion simply goes into the last page if there's room, otherwise make a new page and insert there. Pages, so the effect you get from that is pages fill up. Of course, there may end up being gaps because you've deleted some tuples, so these XXXX represent deleted tuples. And with a heap, we don't generally need overflow pages because we're not requiring that a tuple is associated with a particular page like we are with sorted files and hashed files. The other thing about a heap, and I've mentioned this a couple of times already, in your data structures course you probably would have looked at heaps as a kind of top to bottom ordered tree, or as an implementation of priority queues. That's not what we're talking about here. Simply a sequence of pages that holds tuples. Alright, so given that there's no ordering, the only possible strategy for handling a selection query is to read each page and look at all the tuples in that page and check whether any given tuple satisfies the query. If it does, we add it to the result set. So here I'm giving a little bit details of the reading part, but not much detail on the writing part. Basically, that's going to be write it to an output buffer, and if that fills up, then we dump it to disk, clear it, and start filling it again. Right, but basically for each page, get the page, stick it in a buffer, and then for each tuple on that page, get the tuple, check whether it satisfies. So that's a linear scan. Alright, so the scan is basically from the start to the end. Of course, if you wanted to, you could go backwards, but file scanning tends to work better if you go from the start to the finish. Or if you really wanted to, you could jump around to random pages. But that would be a silly thing to do, given that probably the most effective way of reading a file is from start to finish. Alright, the cost of doing a range query is going to be B. Cost of doing a partial match retrieval query is going to be B. In other words, read all of the pages. The only optimization that we really have available is that if we're doing a one query and we know for sure that there's only going to be a single result, once we've found that result, we can stop the scan. And if we're really lucky, we find the result in the first page and we're done. If we're unlucky, we find it in the last page, or we don't find it at all. On average, we'll find it somewhere in the middle of the file, maybe halfway through. Right, so costs, not really much you can do about it. Alright, insertion into heap files, and here we're talking about heap files in general, not Postgres heaps in particular. But the basic idea here is that we're going to read the last page, put it in a buffer. If it fits, or if the tuple is too big, bigger than a buffer, then we've got to do something to deal with the oversized tuple. Talk about that in a moment. If the buffer doesn't have enough space, then we add a new buffer immediately after the current last page increment the number of pages in the relation, clear out the buffer, which is now associated with the new page, add the record into the buffer, and then write it to disk conceptually. Remember that this get page and put page turns into request and release kind of operation. All right, so the basic idea is you read the last page and you write a new version of that page out, which has the new buffer added, the new tuple added. So one read and one write, and that's even true if we have to add a new page. An alternative strategy, if you remember back to that original diagram, we've potentially got space scattered throughout the file. So what we could do is we could look for a page that has space to hold our new tuple and store the tuple there. If we're lucky, we'll find such a page already loaded into a memory buffer, which would be handy. That would require no read. So what Postgres does is something kind of like this. It looks for a page that's already in the buffer pool from the relation that we're inserting into, and it looks for the most recently modified. And here we're not talking about the SQL update command, we're just talking about general modification of a page. And if we're lucky, we can find one that has enough space. Otherwise, and if that page doesn't have enough space, then we've got to search through the buffer pool, looking for more pages from R until we find one that does have enough space, and then we insert the tuple. Now, Postgres has a mechanism called a free space map, which will help us find a page of R in the buffer pool that does contain enough space. And if there's not such a page already loaded in the buffer pool, of course we have to read it. How do we deal with tuples that are just too large to even fit in a page? Well, we use some sort of external location. In other words, another file outside the data file where we can store these oversized values. And of course in Postgres, we know that's called toasting. Other older systems just have large object locations, files for storing large objects. In other words, large attribute values. So, if we do have a tuple that's oversized, then we need to scan through looking at the individual attributes. If we see something like an int, well, that clearly fits. But if we see a very large value, then we can't store it in the tuple directly. So we put it in an oversized values file and then put a marker into the tuple. That tells us where the object has been placed in the oversized values file. So let's say, for the sake of argument, this is a very long string and we put it at location 1000 in the oversized objects file. So we say, all right, this attribute value isn't located here. It's located in the oversized objects file, and it's there at location 1000. Similarly, if we've got another large attribute value, of course, if we've got attribute values that are relatively small, and there's a threshold for what is relatively small and what is too large, we store them in line. Okay, so ultimately we cannot end up with a tuple that's relatively small, even if it's got large data values for some of the attributes. Right, so what does Postgres do? Well, it's got a function called heap insert. Surprise, surprise. it's inserting to a heap file associated with a particular relation. Obviously, we've got a tuple that we're inserting. We talked about heap tuples before, about the structures. One extra thing that we've got is that well, there are actually a number of extra attributes, but one thing that we need to store is the SQL statement, not the statement itself, but the ID of that statement that's actually doing this insert. So that's required so that we know when the tuple was created. So what does Postgres do? Tries to find a page with enough free space. We said we look in the buffer pool first for an appropriate page. If we don't find one, then we'll get one. Load the page in the buffer pool and lock it. Copy the tuple data into the buffer, and part of copying the tuple data in is to set xmin, which is the start time of the current transaction, the one that's actually doing the insert. This is required for the multi-version concurrency control, as is that. Having modified the buffer, we have to mark it as having been modified. And also the other thing that Postgres has to do is to put information about the insertion into the transaction log. So if this is part of a larger transaction and somewhere along the line the system crashes, we need to know that this, before it commits. We'll talk about transactions later, but if the transaction that is doing this insertion is subsequently aborted, then we need to know that this insertion was done by this transaction and therefore needs to be undone because the transaction ultimately failed. If the relation has object IDs, and once upon a time they were compulsory or they occurred everywhere, nowadays they're optional for relation. What about deletion? Well, deletion involves a condition, so to some extent it's a little bit like a search. So we have to iterate across all the pages in the data file. Once again, we don't know where the tuples are that will satisfy this condition. Get page. One thing we need to do, we need to know whether there were any tuples that were deleted from the current page, and we use that down here. So we only write the page if we actually changed it. And then we iterate through all the tuples in the page, check each tuple. If it satisfies the condition, then we indicate that something was deleted on this page, and then we flag the tuple as having been deleted. Whether that involves actually freeing up the space or whether that involves simply marking the tuple depends on how the particular database implements deletion. Of course, we know that what Postgres is going to do is going to leave the tuple in position but flag it with an Xmax value to indicate that a particular transaction deleted this tuple. The other trick, if we've got if we're deleting on a unique attribute, for example, on an ID, primary key, then as soon as we've done a deletion, then we can quit. We don't need to look at any more pages. So that's essentially just the optimization that we use for selection, deleting when we're done. Alright, so deletion from heaps. We need to know which tuple we're deleting. Now this is the thing that corresponds to delete record. Okay, it doesn't encompass all of this stuff. Simply what we do for a deletion. So one thing we need to do, set X max in the tuple, mark the buffer as having been modified, and update the transaction log. Okay, so it leaves the old tuple in place. We've already seen that vacuuming will eventually get rid of that and compact all the free space. What about updates? Once again, it relies on the condition, so it's going to be something like a search. So we scan all the pages, we replace updated tuples, and we write all of the affected pages to disk. So what's the cost for that? Read all of the tuples. I read all of the pages in the file, and write out just the pages that contain modified tuples. This cost analysis would apply also to deletion. There is one potential complication that when we do an update to a tuple, it no longer fits in the page, or the new version of the tuple doesn't fit in the page. So a couple of ways we can handle that. If there was a certain amount of free space within the page, but was fragmented, we could reorganize the free space and then maybe insert the tuple. If it's still too big, then potentially we need to add another page, or look for another page that does have enough free space. So it doesn't matter whether the updated tuple lives in the same page as the original tuple or somewhere else. So wherever we can fit the new version, we place it. Postgres has, surprise, surprise, a tuple update function. Once again, that's what we do once we've found a tuple that needs to be modified. What it essentially does is delete the old tuple and insert the new tuple. The other thing it needs to do is set the old tuple's pointer to its new version pointer, if you like, to reference the new tuple. Potentially you can do an update in place if this tuple isn't being referenced by any other transaction. So that's a special scenario that may occur sometimes, but it's not the default scenario. Normally you've got someone else poking around in that same relation at the same time. Alright, well, in Postgres, heap files are basically the standard. The tuples in Postgres are called heap tuples. There's a reason for that, is because all tuples are stored in heap files. There are other kinds of files like index files as well. What Postgres will do, if there's a reason to transform a file from a heap file to some other more useful form, for example, sorting it, so that we can use merge join, sort merge join, then we can do that. So we could potentially make a copy of a table during query execution, which has a different structure. And you can also set it as a programmer when you create the file, or when you create the table, or rather when you create indexes on the table. So you could set it up to be a hash file. And that's where you can find details about that. Finally, we've already said this a few times, but a Postgres heap file isn't necessarily just a single file. It may involve toast files, of course, but also even there's not necessarily a single data file. And I've mentioned once the size of a data file exceeds a gigabyte, we create a new file called a fork. And we can add more forks. If we get 2 gigabytes or 3 gigabytes, we get more forks. Also, Postgres heap files often have associated files like the free space map and a visibility map, and maybe a toast file. You can find all the details of how Postgres structures its heap files in chapter 68. So that's it for the simplest possible file structure, heap file.